Assalamualaikum warahmatullahi wabarakatuh. So, in this video, I would like to present about stress analysis on excavator cylinder. Before I go more deeper in this video, I would like to introduce myself and also my group members. So, my name is Muhammad Lukman Hakim, and we have Afrina Miyasara, Ali Farhan, Nur Fasiha Rif'ah, and also Nur Zuhaira Shazwani. Alright, let's get started. This project focuses on the application of solid mechanics in structure. Specifically, we analyze how material respond when external forces and loads are applied. This is important because every structure must be able to withstand forces without failure. For the case study, we chose an excavator hydraulic arm. We focus on the hydraulic cylinder because it is one of the most critical load-bearing components during operation, especially when lifting and digging. Moving on to operational loads, the hydraulic cylinder is subjected to different type of forces, which include compressive, tensile, and also shear force. These forces occur during actual working conditions such as digging soil and lifting heavy material. For the key concept, this project applied important principles such as equilibrium, stress distribution, and material strength. This concept helps us understand how the structure behaves under different loading conditions. And then lastly, for the project goals, our objectives are to analyze the forces acting on the excavator arm, evaluate the structural behavior, and determine the normal stress acting on the hydraulic cylinder, which is excavator arm. So moving on to the next part.
So, for the literature review, we refer to several engineering references related to stress analysis and solid mechanics. According to Beer and others in Mechanics of Materials in 2020, normal stress is defined as force divided by the cross-sectional area, expressed as sigma equals to F over A. This concept is fundamental for evaluating whether a component can safely withstand applied loads. We also refer to Hibbelet in Engineering Mechanics Statics in 2017, who explains that equilibrium analysis and free body diagrams are essential for determining internal forces in mechanical systems. In addition, Su and Yoon in 2016 report that excavator hydraulic system experience complex loading conditions including tensions, compressions, bending, and shear force during digging operations. These references provide the theoretical foundation for analyzing the stress and structural behavior of the excavator hydraulic cylinder in our project.
For the problem definition, our group is evaluating the structural integrity of the excavator hydraulic cylinder during pit digging operation. The core challenge is that the cylinder is subjected to high pressure cycle that induce severe compressive and tensile stress. Any failure in this component will lead to operational downtime and potential safety risk. Consequently, our main objective is to calculate the internal force and determine the normal stress experienced by the cylinder. By conducting the static stress analysis, we aim to verify if the current design provides an adequate factor of safety against structural yielding, ensuring the long-term reliability of the machine.
Thank you to my groupmate for leaving me to explain about my part, which is mathematical modeling and assumption. The free body diagram that we use is cylindrical, treat as two force member, axial loading only. The joint configuration is pin joint at both ends allow rotation while transmitting axial force, and the system state that static equilibrium assumed during peak loading, dynamic effect neglected, and the stress distribution was uniform stress across rod cross section and only valid for pure axial loading. And the force basic that we use is hydraulic force F CYL is equal to P times A piston. For the engineering parameters we used for the operating pressure is 25 megapascal as maximum hydraulic system pressure during the peak digging, and the piston diameter that we take is 150 millimeters at the cap and piston diameter for the fourth generation, and rod diameters is 100 millimeters or 0.1 meter. Cross-sectional area subject to normal stress, and the yield strength is sigma y, which is 250 megapascal for the material yield limit for safety factor calculation, and the stability check, the Euler formula that we use was buckling analysis for slender column behavior. For the extra information, all parameters are based on standard medium-duty excavator specification. The operating pressure of 25 megapascal represent the maximum relief valve setting during the aggressive digging operation. The material yield strength of 250 megapascal correspond to common carbon steel grade used in hydraulic cylinder construction.
Next, I will present the results of our analysis. Using the given operating pressure of 25 megapascals and a piston diameter of 150 millimeters, the hydraulic force generated was calculated as 441.75 kilonewtons. The normal stress acting on the cylinder rod was found to be 44.98 megapascal. This value is much lower than the material yield strength of 250 megapascal, showing that the cylinder can safely withstand the applied load. The factors of safety obtained was 5.56, which is well above the minimum recommended value of 2. This indicates a strong and reliable design.
Alright, now I will move to the sensitivity analysis and discussion. First, for the safe operation, the calculated normal stress is 44.98 megapascal, which is significantly lower than the material yield strength of 250 megapascal. This confirms that the hydraulic cylinder is operating well within safe limits. There is no risk of immediate failure. Next, for the safety margin assessment, the factor of safety obtained is 5.56 is considered quite high, indicating that the design is very conservative and has a large reserve capacity beyond the expected working load. Moving to pressure sensitivity, when the operating pressure is increased to 35 megapascal, which is about a 40% increase, the factor of safety decreased to 3.97. However, this value is still above the minimum acceptable limit of 2.0, meaning the structure remains safe even under higher pressure condition. For the dynamic shock buffer, the high factor of safety also provides an advantage where the system can withstand unexpected dynamic loads or shocks, especially during rough or uneven terrain operation. And lastly, for future optimization, since the safety margin is quite large, there is potential to improve the design by reducing weight. This can be done through the material optimization or refining the geometry without compromising safety. To summarize it, even under increased pressure condition, the design still maintain a strong safety margin, confirming that the structure is reliable and robust. That's all for the discussion section.
In conclusion, our study successfully determined the stress acting on the excavator hydraulic cylinder and verified that the design is structurally safe. The high factor of safety provides additional protection against unexpected loads and helps ensure operator safety during operation. That's all from us. Thank you.